Let's jump into the lab, and today we'll be working on the point-to-point between router 2 and router 4. So here we want to enable BGP on router 4, and we simply do that by typing router BGP, and let's say our autonomous system number is 10. Now we want to establish a neighbor relationship with router 2 to their serial interface. So then we type in neighbor, the IP address of our neighbor, and then the remote AS, and we'll say their remote AS is 10 as well. So this is an iBGP connection, which we will talk about later, but basically we're connecting two routers in the same AS, and there you see our neighbor is not up. We see it in our BGP table, but it's not up and active because we have not enabled it on router 2. So on router 2 we type router BGP 10, the neighbor, the IP address for router 4, and now we should see this neighbor relationship come up. And it may take a second here. There we go. So now the BGP neighbor relationship has come up between router 2 and router 4 simply by entering two commands on each router. We now have a valid BGP configuration. Now when I show iPBGP, which shows the BGP table, or show IP route, we don't see any BGP routes being shared because we're not inserting anything to BGP just yet. So how do you advertise networks? You can do it many ways. You can do it through propagation of received BGP routes that you're already receiving from someone else. You can redistribute routes into BGP. You can source the routes from your actual router, and you can do that by using the network command, which would specify the exact network you would like to insert into BGP. And there needs to be a match for that in the local routing table. Or you can use the aggregate address command, which does what it says. It aggregates multiple routes into one larger route. So here's an example of the network command: router BGP autonomous system, and then the network 192.168.1.0/24. We want to advertise that route, and that would do it. Now, what is the BGP table? At a high level, the BGP table contains all learned BGP prefixes. So it takes all the learned prefixes from all neighbors, and then from there it chooses the best path from those options. And that is the route that it advertises to its neighbors. So let's go ahead and take a look at the topology table and the contrast between different types of routes and the effect that the topology table has on the routing table. So let's do a show IP EIGRP topology, and here you can see that one route has a better feasible distance than the other. That one entry will be the chosen path, the successor, and there's one entry in the routing table, even though there are two entries in the topology table. That's in contrast to this other route, 192.168.40.0, where we have two entries in the routing table. Here's another IP version 6 address. How do we break it out into subnets? Well, here you have it. We're honoring the first 48 bits of this range, and then we are breaking this out into smaller subnets, as you can see here. Each subnet matching the first 112 bits. Now here are some frequently used commands for IP version 6 addressing and rolling it out. Specifically focus in on IP version 6 address and the address length, and that is the static configuration of the IP version 6 unicast address. So here we have our lab, and today we'll be working on router 2 and router 4. Router 2 connects to area 0, and between router 2 and router 4 is area 1. So for area 34 to communicate with area 0, which is a requirement, we need to set up a virtual link, and we'll do that right now. So here we are on router 2, and we type router OSPF 10. And when you create virtual links, you want to specify the router ID, because virtual links reference the router ID. So we want to make sure we actually specify that in OSPF. And we're using loopback 1 for each router 2 and router 4. Now in router 4, we go to router OSPF and then area 1 virtual link, and then we use the router 2 router ID 192.168.20.1.